Hello everyone, my name is Syed Afrooz from Section D of AIML and my rule number is 24951 Today I am going to explain about uniform transport waves of PDE and from the subject of differential equations and vector calculus. So what is uniform transport waves of PDE? First of all, we will know the what is PDE and its introduction. Uniform transport waves are a type of solution to certain partial differential equations. They describe the propagation of waves or signals in a homogeneous medium. Understanding these waves is crucial for applications in physics, for engineering and applied mathematics. So we will see what is partial differential equation, that is PDE. Ordinary differential equations have only one independent variable. For example, 3 dy by dx plus 5y square is equal to 3e minus x and y of 0 is equal to 5. Partial differential equations have more than one independent variable. For example, 3 dou square u by dou x square plus dou square u by dou y square is equal to x square plus y square, subject to certain conditions, where u is a independent variable and x and y are the independent variables. So we will see what is definition of transport waves. Transport waves refers to solutions of PDE that maintain their shapes while moving. These waves can be characterized by their speed and direction of propagation. Transport waves are typically described by first-order linear PDEs. The first-order PDE has its general solution u of x comma y is equal to f of 2x minus 3y plus 1. For arbitrary function of s, the PDE could be A. 2 dou u by dou x minus 3 dou u by dou y plus 1 is equal to 0. B. 2 dou u by dou x minus 3 dou u by dou y is equal to 0. 9 dou square u by 9 dou x square minus 4 dou u by dou y square is equal to 0. And these are the some examples of PDE could be in arbitrary function. So we will see the next topic, that is mathematical formulation. The standard form of a transport equation is u t plus cux is equal to 0. That is equal to here. Modulus of u is the wave function and the modulus of c represent the wave speed. That subscribes denotes derivations. The solution the solution to this equation exhibits uniform transport properties over time. And the next characterizer for transported waves. Transport waves are characterized by their constant speed and directions. These maintain their shapes as they propagate through shape. The uniform makes them ideal for modeling various physical phenomena. Initial conditions. Initial conditions play a critical role in determining the behavior of transport waves. The initial profile of the wave influences its propagation overnight. Common initial conditions include step function and sinusoidal shapes. And the next one is the method of characteristics is often used to solve transport equations. This approach transforms PDEs into partial differential equations into a set of ordinary differential equations along characteristic curves. Solutions can then be traced along these curves to understand wave propagations, wave speed and direction. The wave speed mod c determines how fast the wave travels. Positive modulus of c indicates propagation in the positive x direction, while negative modulus c indicates the opposite. The direction and the speed of transport waves are critical for applications in fluid dynamics and signal processing. Uniformity of transport waves. Uniform transport waves maintain their form regardless of time. This uniformity simplifies analysis and predictions of wave behavior. The concept of uniformity is essential for applications in communications and material science. So these are the ABCD or surface morphology of tin films made with different sputter puffs, A of 2 kilovolts and the B of 4 kilovolts and the C of 6 kilovolts and the D of 8 kilovolts. Cross-sectional image of tin films with 2 kilovolts power. And we will see applications in physics of PDE transformation of wave. Transport waves are used to should model sound waves in acoustics. This they also plays a significant role in fluid dynamics, particularly in describing flow patterns. Understanding these waves aids in prediction behaviors of physical system under various conditions. So next, applications in engineering. How it is useful in engineering in present situation and the future synopsis. Engineers utilize transport wave concepts in designing communication systems. These are critical in analyzing wave propagation in electronic circuits. Applications extend to structural engineering, particularly in understanding stress wave propagation. These are concepts and designing in engineering. So numerical method of transport waves. So the various numerical methods can approximate solutions to transport equations. Finite difference and finite element methods are commonly employed. These methods provide insights into complex wave behaviors that are difficult to solve analytically. Forward difference, backward difference, and central differences graphs are given below. F of x on the y-axis and appropriate slope on the true slope on the x-axis. So we will approximated slope, true slope, and approximated slope are the three color lines. So we can see here the graph. And the next one is stability analysis. Stability of numerical schemes is crucial when dealing with transport equations. Analyzing stability helps in preventing numerical artifacts that can distort wave behavior. A stable scheme ensures that the numerical solution converges to the true solution over time. And this is the graph and the scheme of stability analysis from the years ago. So next one is comparison with other wave types. Transport waves differ from standing waves in that they do not oscillate in space. Unlike dispersive waves, transport waves maintain their shapes during propagation. Understanding these differences is important for accurate modeling in various fields. So next one is limitations of uniform transport waves. Uniform transport waves assume a constant medium, which may not always be realistic. Real-world applications often involve non-linear effects that can complicate wave behavior. Understanding these limitations is important for accurate predictions in practice. The next one is non-linear transport waves. Non-linear transport equations can exhibit more complex behaviors than linear ones. These equations can lead to phenomena such as shock wave and solitons. Investigating this effect results requires advanced mathematical techniques and numerical methods. Analytical solution. Some transport equations allow for analytical solutions under specific conditions. Techniques such as Fourier transform can be used to derive these solutions. Analytical solutions provide valuable insight into the wave properties and behaviors. So next one, case studies. Case studies illustrate the application of uniform transport waves in real-world scenarios. Examples include modeling traffic flow and analyzing wave behavior in oceanography. These studies highlight the practical relevance of wave theory, and these are the some characteristics of CCT program in the selected countries. So the table is given below of OVE and the future directions in research. Ongoing research is focusing on extending transport wave theory to complex media. There is also interesting in developing more robust numerical methods for simulations. Future advancements may enhance our ability to model and predict wave behaviors accurately. And the conclusion is uniform transport waves represent a fundamental concept in the study of PDE. This application span various disciplines, underscoring the significance. A deeper understanding of these waves can lead to advancements in both theory and practical applications. And the partial differential equation PDs, these are the reviews and the journalism report given for the last years. And thank you for giving this opportunity.